Welcome back. This is our next topic that we're going to start talking about, which is circular motion. We've been through the idea of vectors, we've been through inclined planes in various forms. Now we're looking at circular motion. This comes from the Queensland physics syllabus from Unit 3. All right, what are we going to do today? We're going to look at uniform circular motion, describe how it works. We're going to start to talk about things like a velocity and a period for an object in circular motion, as in an object moving around in a circle, and solve a few problems. And then we're going to start to understand the forces involved before next episode, where we will actually calculate the forces. Our little infographic on the right there shows us how over the course of 4.5 billion years that Earth's been around, the length of a day is getting longer and longer and longer. So it means the rotational speed of the Earth is actually slowing down. And this is usually due to things like the tides and so on, and water and whatnot moving around the Earth. Just various sort of frictional effects like that are helping to just slow the Earth down ever so slightly over time. So when the dinosaurs died out 65 million years ago, we had 23 hours in a day. Now we've got 24. In years to come, it'll get longer and longer. Always wanted more hours in a day. Okay, so from our curriculum, we've done that top part. Now we're starting to deal with this stuff down here. We're going to start looking at circular motion. We're going to start to introduce a few formulas, and obviously there'll be a couple of calculations that come with that. Just a few little definitions around uniform circular motion. We're talking about an object moving in a constant speed in a circle. So that's the idea of something revolving around another object or something else. So think of the Earth revolving around the sun once per year. That's different from a rotating, where something's rotating on its own axis. So the Earth itself rotates on its own axis, and this forms the days. Our little fidget spinners down there are rotating on their own axis. That's a rotation. But we're talking about revolving around in a larger circle, often around something else, but not always. So uniform circular motion is an object traveling in a circular path at a constant speed. It's going through this uniform circular motion. But the object's motion is constantly changing. So because it's constantly changing direction as it moves around a circle, so like around this blue circle is where an object's moving around. Because the direction is changing, that means the velocity is constantly changing. Because the velocity is constantly changing, there must be some sort of acceleration, and there is obviously a force applied in order to do that. What we'll concentrate on today is just that change in velocity that I'm showing with the green arrows there. Incidentally, we are talking here about circular motion in terms of horizontal circular motion, because when you're talking about vertical circular motion, as an object sort of goes up and down in a sort of a vertical plane, there is the force of gravity that affects the object going up one side of the circle and down the other side of the circle. That's not really part of the course we're dealing with. We're only dealing with horizontal motion around that plane, so gravity doesn't apply. Right, so the velocity of an object in uniform circular motion is directed as a tangent to the circle. So that's what we sort of said here. That red ball is traveling in the direction of the green arrow at that instant. At that point, it has this force applied, this centripetal force as we call it, that is accelerating it towards the center of the circle. The force or the acceleration is towards the center of whatever it's moving around. And that's what keeps it moving in a circle. You can almost think about this vector and this vector kind of resolving together to form this circular path around here. It should be noted that once that force is gone, the object will continue in whatever it's doing at that instant, which is traveling in that velocity at the tangent to the curve, so it travels straight off that way. All right, that force towards the center has got to be there the whole time, and that is the centripetal force that keeps this thing in motion. The force is always at 90 degrees to the direction of the velocity at that instant. If we look at how this sort of all comes together, if we look at part of our circle, now the change in velocity is simply a final velocity minus an initial velocity. So if I look at my little circle over on the left-hand side here, let's assume the object is going from that location there to that one over there. So my final velocity is going to be this one here, which is that vector going that direction, which I've drawn here. My initial velocity is this vertical vector here, which is that vector I've drawn there. And my formula said change in velocity is final minus initial. That's what I've done here, my final minus initial. Now to make it easier so we can add some vectors together, the opposite of minusing that vector that goes up is adding a vector that goes down. It's kind of like I reversed both of them to still make it true. Now I've got two vectors that I'm adding together, and it's like I can take one of them, say this guy here, and put him up there, and I end up with that diagram over there. Now I have head to tail addition, so head to tail of the two vectors, and I can draw them together as a right angle triangle, and this is now my change in velocity, which is depicted right there on my diagram. The change in velocity between my first location here and my second location over here is that change in velocity there. So that's kind of like explaining what's going on. The velocity must be changing towards the center of the circle, so there must be a force applying some acceleration towards the center of the circle. That's what keeps the object continually revolving around. Think about other examples. You can swing something around on a string, like a ball on a string. It is the string that constantly applies a force back towards your hand to keep that object moving around in a circle. The Earth rotates around the sun, as is in every year. We move around the sun. That's 1 year. It is the gravity of the sun that is applying that force on Earth to keep it doing that. The Earth has this massive sideways velocity, but then it's the force of the gravity of the sun that pulls the Earth back towards the sun, and what we see is this stable orbit all the way around the sun. So when a force acts on an object, it causes the acceleration, therefore the velocity changes in the direction of that applied force. And this force is always towards the center. So we can call these forces, force with the lower c there, centripetal force, and that's going to cause a centripetal acceleration. All right. The velocity is always along that outside of the circle. The force is like this radius almost of the circle, from the center of the circle out. That is where the force is being applied in that orientation, which is also the acceleration. We think about another example here, like a gravitron. All right, same deal. You're in this uniform circular motion as you move around it. It's this sort of ride that we've shown here where people lie up against the wall and so on, and it spins around and around and around circles really fast. Lots of fun. Lots of fun till someone gets sick, that is. But anyway, lots of fun. Now, this is the same sort of thing. You've got a sideways velocity that is making you travel around. But if we look at that bloke there, riding like a boss, he basically, in this scenario, has a force of his weight pushing outwards. But every action's got an equal opposite reaction. There will be a normal force pushing him back, holding him where he is. And that normal force is our centripetal force that keeps him in motion there. All right, so what we've done is there's our forces acting on that bloke there. That's what we've just been through. We've got the sideways velocity, we've got the weight pushing out, and the normal force in response to that. So, period. The period is something we define as one complete cycle. So when we're talking about one complete revolution or one complete moving around in a circle in uniform circular motion, that's the period. We've discussed periods before when we talk about things like a pendulum is the time it takes a pendulum to swing across and back again. But in this case, period is one cycle, one complete moving around in the circle, one revolution. So period is capital T is the symbol for it, and it's a time period, so the standard units would be seconds. We have a total time here that we're going to come back to, which is obviously time in seconds, and the number of revolutions that we actually had. So my formula is down here. The period is the time elapsed divided by how many revolutions that we had, and that will give you the period, which is the time for one complete cycle. I warn you, this is not in the formula book that we use, that data book there, so you need to remember this one. Total time elapsed divided by the number of revolutions, that's the period or the time for one cycle or one revolution in this process. We need that because we need it in calculation of velocity, so centripetal velocity. So velocity is 2 pi r over t. It's basically a calculation derived from the circumference of a circle and the time it takes to travel around that circle, because speed is distance over time effectively. That's effectively what this is. Speed is velocity, distance is 2 pi r, which is the circumference of a circle, over the time, which is the period in this case, the time for one revolution. This guy's in the formula book. You need to know how to use it. Don't forget your standard units. Your radius is always in meters. No matter what you're given in the question, go to meters. Time in seconds, you will get a velocity in standard units of meters per second. Let's look at an example. Determine the velocity you are traveling as the Earth rotates on its axis. So we're going to need our velocity formula here. In order to do that, we're going to need to know the period. Well, the period of a rotation on Earth is just 1 day, 24 hours. We can convert that to standard units of seconds. And we need to know the radius of the Earth. So here's our formula, our constants over here. The radius of the Earth, 6370 kilometers or meters, is written like that. Convert 24 hours into seconds, 86,400 seconds. That's what you've got each day. So they plug into our formula. 2 and pi are constants. Got my radius over there. I've got my period that I worked out over there. Here's my mathematical reasoning there when we're working out. Plug it in your calculator and it all comes out in the wash. 463.2 meters a second is what you are traveling right now, sitting on this planet Earth. A little bit faster than you can run. Let's look at another example. Do a comparison. Comparison of spin dryers. So a spin dryer removes the clothes from your in your washing cycle by spinning really, really fast. So it's obviously an example of circular motion here, uniform circular motion. So it says in our question here, it is suggested that if you can increase the speed of a dryer by doubling the diameter or doubling the rotational speed. So let's have a look. Dryer A has a radius of 50 centimeters, 0.5 meters, and it does 12,000 revolutions per minute. That's not a period. In 60 seconds, it does 1,200 revolutions. So you need to work out the period. Dryer B, we've got double the radius, so it's a much, much bigger machine, traveling at half the speed. Okay, so determine which one's got the highest speed and which one's going to work best for our household laundry. Justify a response. When you're doing this, just have a look. I mean, that's got 2 marks, so you really want to have 2 clear points here. Otherwise, there's no possible way you can get 2 marks. If this is worth 4 marks, then there must be 2 marks for working out the speed of the first dryer, dryer A, and the second one for the dryer B. Rightio. First things first, write down what we know. So the radius of A is 0.5 meters and it's 1,200 RPM, and B is 1 meter and 600 RPM. And we've got our 2 formulas there. So the first thing we can do is work out a period. Now, yeah, sure, you can do it in minutes like that, but that's pretty useless because we want standard units of seconds. So in a 60-second minute, it does 1,200 revolutions. So each revolution is 0.05 of a second. Now, we can take that and chuck it into our formula here. We've got the radius here that came up the top that we had from that question, and we'll go straight into the velocity calculation. 2 times pi times 0.5 over 0.05. Put it in your calculator. We're traveling 62.8 meters per second. A little bit fast. That's a pretty average sort of dryer, these two. There's nothing special about these guys. Just have a think. 100 kilometers an hour is about 27, 28 meters per second. So very, very fast. So now we're going to do the same thing with the other dryer. Got to work out the period and work out the velocity of that so we can then compare the two. So period in 60 seconds, it does 600 RPM. So 60 over 600 is 0.1 seconds. So it takes 0.1 second to do one complete revolution, one complete rotation around it, sorry. What we really want is the velocity calculation, which is down here. So we plug our numbers in. The radius is the meter, the period is 0.1, we get 62.8. So they both have the same speeds. They both have that same velocity around the circle as each other. That's the first part of the question. The second part, which one's better? Which one's better for your clothes? And if we look at our explanation down here, that's written quite nicely from the textbook, As they both have the same speed, the drive with the smaller radius is preferred. It will have a greater change in velocity or centripetal acceleration as it is moving in a smaller circle. And we'll see when we start to look at the formulas here, how the change of radius affects the force and the acceleration on it. But the smaller one is going to have the greater change in velocity, so therefore it's preferred. Thus, the clothes are being pulled away from the water with the greater centripetal force, because if you think about our circular motion, if the clothes are here, the water will continue to go in a straight line while the clothes have the force of the drum turning them around. So it's effectively the clothes being pulled sideways whilst the water undergoes with its own inertia, just keeps going straight ahead, and it separates them out. And note the direction that the water comes out of that drum. It doesn't go out as in out that way, it goes out that way. Okay, good example of this, particularly in science laboratories and so on, is a centrifuge. We often use centrifuges to separate out things. As you can see, we have little tubes like this, and we stick it in this little rotating platform thing here, and we spin it really, really, really fast. Now, the substance that's in our tube will typically separate out according to density or mass, or depending on what it is, the reaction that we're trying to do. Heavier stuff, like if you get, say, blood, for example, that might be an example of something like that. It could easily spin at 1,000 to 5,000 RPM. The denser particles are going to separate out to the bottom like they have down there, and the more liquid parts of your blood will be at the top there, and hence we can separate out the red blood cells and so on from the rest of it. We can do the same sort of thing with things like DNA and stuff like that to purify samples in biochemistry. Works the same sort of way. Okay, so that brings us to the end of today. We've spoken a bit about the velocity or the speed around in circular motion, what it actually is, the period. Don't forget, there is a force applied towards the center of rotation to make this thing keep moving in uniform circular motion. We've got a few more ticks on our thing here now. We've spoken about this guy here. We've spoken about speed and period. We've done the velocity calculation, so acceleration and force are still to come. The best thing you can do right now, have a crack at doing some questions out in the textbook or the worksheets you're given, and see if you can get these ideas in your head. This is the one that we've done here, so 2 more to go. Okay, thanks a lot for coming, and see you next episode.